Okay. Welcome everybody to the August 2021 technical presentation of IEEE MTT-S Santa Clara Valley San Francisco Joint Chapter, also known as MTT-SCV. My name is Sutkashwini Krishna. I'm the chairman of this chapter. And the title of today's talk is, it's a very interesting talk indeed, Terahertz communications at 300 gigahertz, devices, packages, and systems. And we are very fortunate to have with us today Professor Ho-Jin Song, who is the Associate Professor of Electrical Engineering at Pohang University of Science and Technology, also known as POSTECH in Korea. He is also a distinguished microwave lecturer of the MTT Society. So welcome, Professor. The agenda for today's talk will be, we'll start with some meeting notes, followed by a quick COVID-19 update. We will look at the list of current officers and also talk a bit about upcoming elections for next year's officers. Then we'll go on to the details of the talk itself, and that'll be mixed with the Q&A as we go along. So to present the meeting notes, I would like to call upon Mr. Tom McKay. Tom is our vice chair. So Tom, take it away.
Thank you, Akarsh. So a few things to note. This meeting is being recorded and live broadcast on Zoom. Links to the recorded video and slides will be sent to all registrants after within a few days after the talk. We are keeping all cameras off and microphones muted. When you ask questions, if you can push the raise hand button, reaction button, then the host can unmute you to ask your question verbally. Please ensure that your display name in Zoom matches the one that you use to register. This allows us to ease the check-in process, which is very important for the chapter to be able to record, the attendance list. So thank you very much for that. We are a part of the IEEE, the Institute of Electrical and Electronics Engineers. Our byline is Advancing Technology for Humanity. And the IEEE and its members inspire a global community through highly cited publications, excellent conferences, technology standards, protocol standards and other things, and professional and educational activities. The Microwave Theory and Technique Society focuses on the theory and applications of radio frequency, guided wave, and wireless technologies. Please support us by becoming a member. You can join the IEEE at ieee.org/membership, and you can join the MTT at mtt.org/join-mtts-s-o. Thank you very much. You can also follow us on LinkedIn with the hashtag MTT-SCV. We're all in-person meetings related to our chapter are canceled. Our technical monthly meetings are being held in webinar online format only, and that includes officer meetings, which occur monthly. The 2021 chapter officers are Utkarsh Unikrishna, the chair. I am Tom McKay, the vice chair. Venkata Gade is our secretary, and Tan Tu is our treasurer. The nomination period for 2022 is through the end of September 2021. If you're an MTTS member in good standing from the Bay Area and wish to serve as an officer, please contact JS Banwait at ieee.org with your name, position of interest, your IEEE membership number, and your phone number and email address. Okay.
Thanks, Tom. So next we'll go on to the details of the talk itself. So the title again is Terahertz communications at 300 gigahertz, devices, packages, and systems. Our speaker today, as I mentioned before, Dr. Ho-Jin Song. who's a distinguished microwave lecturer of the MTT Society. So a little bit of information about him. So he joined Nippon Telephone and Telegraph, also known as NTT, in 2006, the third largest telecom company in the world. And he is engaged in a variety of activities related to development of sub-millimeter wave and terahertz wave devices, circuits, and systems for various applications. In 2015, he was named to a distinguished research scientist position of NTT Labs. Since 2016, Dr. Song has been with the Department of Electrical Engineering at Pohang University of Science and Technology in Pohang, Gyeongbuk, Korea. His current research interests include millimeter wave and terahertz circuits, antenna packages, and testbed systems for a variety of applications. He's also won a variety of awards listed there. He's also a senior IEEE member and DML for the 2019 to 2021 term. So a little bit of detail about the talk itself. So as the title suggests, we'll be looking at basically terahertz communications at 300 gigahertz and above. So basically in this talk, we'll be looking at the first prototype of a terahertz wireless communication system designed under the touch and go scenario. Dr. Song will then clarify the concept of the kiosk data downloading system, cover some considerations in this work, and present a brief link budget plan. We will then overview technologies for implementing terahertz components operating at 300 gigahertz and their performance, followed by an investigation of channel responses and experimental demonstration results. And towards the end of the talk, we will discuss several issues that need to be addressed for the future of terahertz communication systems in terms of system architectures, packaging, and potential applications. So very interesting stuff indeed. And with that, I will hand off to you, Professor. You can start sharing and take it away.
Okay, thank you for kind introduction. And but my screen, I cannot see my screen. Just give me a second. All right.
No worries, Professor. Take your time.
Okay, thank you very much for your kind introduction, and thank you everyone for joining in this virtual session. Today I'm going to talk about the terahertz communication system, and particularly we have when I was in Japan, NTT, we had a big project that is about the kiosk data download system that provides more than 20 gigabit per second in real time. And during that, we found that there's several issues in device and packaging, particularly and also several new challenges in system design. So basically, I will show the detail of that project and the result, and then probably we have some issues or the point we need to discuss for next phase, terahertz communication system, or maybe 6G communication system.
Professor?
Yes.
McKay, I'm not seeing your slides.
Yeah,
really?
we don't see it. Yes.
All right. I'm sorry. Probably I need to share it again.
There we go. Perfect.
Yes.
Thank you.
Right. Okay, before getting to the detail, I'd like to briefly introduce my institute, Pohang University of Science and Technology. So here is a map of the Korea, so south part and north part, and as you may know, that Seoul is located around the middle of the Korea, and now Pohang is just around here. And basically, the Pohang is very well-known city as steel and technology. So there is one of the biggest steel company in Pohang, and actually this company, POSCO, founded this POSTEP 35 years ago. So they are basically financial supporter of this university and all my research in POSTEP. And okay, so here is my group. All right, so here is my colleagues I'd like to give my special thanks to. And first of all, I'd like to briefly introduce why we are so interested in terahertz frequencies or frequency band for communication system, and then briefly introduce the history of the period works of the terahertz communication system worldwide. And then a little more detail of the full system demonstrations in kiosk data download system scenario. That is actually a very simple one. So we introduced ASK modulations at 300 gigahertz, and then we realized that there is a couple of issues, particularly in packaging. So I like to introduce what we did, and it will be quite exciting, some of you. And then before concluding my talk, I like to share some new challenges I realized, and then hope to discuss with you. All right. The terahertz band is, as you know, the okay. The terahertz wave is, or frequency is basically locating right between microwave and the light wave in electromagnetic spectrum. And in terms of spectrum, probably the 100 to 10 terahertz can be set at terahertz frequencies. But anyway, from the microwave side, the terahertz wave has very high frequency and short wavelengths. On the other hand, from light wave side, the terahertz wave has very long wavelengths with very low energy. So based on that, because of such a features, many people try to use this frequency band for a spectroscopic system by using the rotational, vibrational, or transitions of very large molecules. And also, also because of short wavelengths compared to microwave or millimeter wave, probably we can have very fine resolution imaging system or radar system. But it was quite hard to utilize the terahertz frequencies for a long time. That's because of the very low powers in this frequency region. So maybe we can use electronic devices, but as you can see, the older devices may provide much less power at terahertz frequencies. And also the radio system can radiate at terahertz frequencies, but the output power is very limited. But the reason why we are so interested in terahertz frequencies for communication system is just because of large bandwidth. This is something like a height for basketball players. As you may know that there are many features are required for good our best basketball players, such as speed, strength, or something else. But in case of the speed and strength, it can be gained by practice or even medical treatment, but the height cannot be gained more. So bandwidth is something like that for communication system. We can enhance the power, or we can reduce the noise from the system by using dedicated devices or circuit, but it is quite hard to get more bandwidth once frequency is allocated for specific applications. Or yes, so that is a reason why we are so interested in the terahertz frequencies. And also, if you look at this channel theory, the maximum capacity is simply bounded by the bandwidth and the signal to noise ratio, or output power of the system. So in many contemporary wireless communication systems, they are working in this, let's say, a bandwidth limited region. So usually the bandwidth is once limited, but to get, to send more data within a time, we had to increase the output power or signal to noise ratio, to accumulate more bit in single frequencies, given frequency band. But there is another way to increase the bandwidth according to this equation, simply by increasing the bandwidth. So in theory, we used to say that the power limited region. So if this means that even if the power is limited, we would be able to increase or enhance the data capacity by using very huge bandwidth. I'm not sure that the terahertz communication system will work in this power limited region, but at least I can say that it might be something different with that the bandwidth limited are the other wireless communication system operating in this bandwidth limited region, maybe somewhere intermediate position between this. Okay, the one biggest concern of the Terahertz communication system is actually the attenuation loss in the air. I plotted the attenuation loss at up to 3 terahertz, and as you can see, we can see now very peaky absorption lines at very high frequencies, and also the attenuation loss itself is very high. So it might be quite difficult to use this very high frequency band at above 1 terahertz for communication system. But if you look at the frequencies below 1 terahertz, then of course, yes, there are a couple of there are several absorption lines, but right between those peaks, we can find very clear and low loss windows. So I summarize those windows in table. And for example, if we can use 300 gigahertz band, then the 40 gigahertz a very clear window would be available. And if we can increase the carrier frequency at up to maybe 700 or 800 gigahertz, then more than 100 gigahertz clear window will be available. And also the attenuation loss itself is not that bad. So now the older windows provides much less than 0.1 dB per meter. So assuming 100 meter communication system, then the 10 dB loss is expected even for the heavy rain condition. And if we are considering short-range communication system or indoor communication system at up to maybe 10 meters, then attenuation loss in air will be much less than 1 dB. So in that point of view, at least we can consider this frequency band for very short-range communication system. And in that point of view, many people look at several potential applications, such as, of course, Wi-Fi or Bluetooth or WPAN, and also last 1 mile system at outdoor conditions. And kiosk data download system is what we did in past. So probably I have a chance to talk about this a little more detail. And in case of the backroad system, so we are considering long-range communication system, but this is fixed point-to-point communication system. So as you may know that particularly in the these 3 applications below is kind of the so what we are thinking is maybe we can replace fibers in specific applications. So in case of the antenna station or backhaul link, so as you may know that in 5G 4G system, the 4G system operating in microwave frequencies, so that the density of antenna station itself is not that high. But when we increase the carrier frequency for 5G at up to 28 or 36 gigahertz, then because of the millimeter wave operations, we need to increase the density of the antenna stations. And also, to provide very high throughput of the 5G system, the feeding data throughput should be as high as 10 to 100 gigabit per second. So basically, we need to use a fibers connection to the antenna station. But again, because of very high density of antenna stations, it is quite hard to do that, to make such a feeding network, data feeding network with the fibers. So we are now, many people are thinking how we can feed the data in wireless manners. So the only problem is then how we can provide 100 gigabit per second wireless data transmissions. And simply to achieve such a high data rate in wireless condition, maybe we need to increase carrier as high as 100 or even more. So in that point of view, Terahertz communication system can be, or simply Terahertz data transmission system can be used in fiber backhaul system or fronthaul system. And also data center is one of the very attractive applications for Terahertz communication system. That's because it is not the typical, so it is maybe intended portals, to show the demerit of the fiber connections. But anyway, the many data centers, the servers are connected with the plastic fibers. But the problem, what I heard from that community is that because of plastic fibers actually is not that flexible in terms of network configurations, and also it causes very massive maintenance task. So some people are looking at how they can are looking at some wireless link between the servers. So the wireless communication in data center is one of the very hot topic in communication society. Again, the one problem is what is then the appropriate wireless communication devices or system which can be replaced with fibers. The issue is throughput. So the wireless communication system or link should provide as high as, again, the 10 to 100 kbps per second. And in order to do that, maybe we need to increase the carrier frequencies. And the other one is, yes, the other one is the device-to-device communication system, for example, the CPU and memories. So the throughput or the required bandwidth between the CPU and the memory is reaching around a couple of terabit per second, even at this moment for your personal computers. But those data channel is now provided by very low-cost copper-based PCB technology. But already the limitation is reached so that in processor or RAM, very high-ended RAM, we need to introduce the equalizer I/O part. Actually, that consumes lots of powers. So many years ago, Intel tried to replace that with an optic link on the PCB. And also some people these days looking at some other way to provide very high data throughput data channels between CPU and memory in wireless manner. Again, so I said a couple of terabit per second should be provided in these applications. And then if we provide that in wireless communication, wireless means, then the carrier frequency should be very high. So that is actually the reason why we are so interested in the Terahertz communication system. Well, so it is quite hard to say how then large data capacity is required for any specific applications, but let's assume that anyway, in somehow 100 gigabit per second will be necessary in near future. Then how we achieve that? So according to the communication theory, the bandwidth is basically defined by the number of antenna and modulation or spectral efficiency and bandwidth. So one may use a very narrow bandwidth of around 1 gigahertz with a very complicated modulation scheme, such as 1000 QAM with 8 antennas for transmitter and receivers. Then the 80 gigabit per second will be theoretically achievable. But in my case, I rather use a wider bandwidth around 50 gigabit per second with a very simple modulation scheme such as QPSK with the single antennas. Then this configuration may provide 100 gigabit per second. So I'm not sure that which configuration or which design is better for 100 gigabit per second. But anyway, this calculation, simple calculation actually indicate that large bandwidth is very advantageous in terms of the complexity of the system itself. So in that point of view, once we need to increase the bandwidth, maybe we need to rely on the complicated modulation scheme with the MIMO system. But most important thing or the biggest technical challenge at this moment is how we can increase the carrier frequency or how we can define the large bandwidth. So the simple way is increase the carrier frequencies. This is okay. So as far as I know, the very first data transmission experiment at Terahertz frequency had been conducted in 2004 by a German group. At the time, they used to use a spectroscopic system as a transmitter and receivers. Simply, they inserted one dedicated devices for data or Terahertz signal modulations. So they fabricated the two-dimensional electron gas modulator, actually a very simple substrate, and then they applied some voltage in the device, and then they try to modulate the actually Terahertz pulses. But problem was that because of very limited operating bandwidth of these modulators, they were not able to send very huge data, even on the terahertz frequencies. So since then, many people actually looked at how to prove the merit of terahertz communication or terahertz frequencies for communication system. So in my group in Japan, we used to use a laser or photonic transmitter technique. Actually, what we had is just two laser diode and one dedicated devices, which is called the photo mixers. So if we inject two laser diode, then this photo mixer will produce the electromagnetic wave of which frequency is correspond to the frequency difference of the laser diode. So based on that, it is quite easy to modulate a high data rate signal by using electro-optic modulators or any optical or photonic modulator, which is used for telecommunication industry. So based on that, we built up the system, and here is you now seeing the transmitter, and here is the receivers. So I didn't mention that here, but anyway, in this experiment, we used to use OOK or ASK modulation scheme, so that the receiver in the receiver side, the simple single diode receiver was used, and here is a photo of the receiver. Actually, it is quite hard to say the receivers because the single antenna with the single antenna is all. There is no amplifier or there is no post amplifiers. So single diode detector has been used for a receiver, and this is a result. So please note that the link distance was at the time was around 50 centimeters. And since the output power from photomixer was very limited, we had to use a plastic lens. The single lens was provided around the 50 dB gain in the link. Anyway, so from this experiment, we were able to get 24 gigabit per second error-free data transmissions. So the error-free in this talk, error-free mean in this talk is we didn't use any signal processing technique, no equalizers, no feed-forward collection, feed-forward error collections, or so anyway, or even with no bit reshaping circuit. So really low data received by this single diode receiver was look like that, and the error-free transmission has been achieved. So please note that the 24 gigabit per second data rate is a very high data rate at that time. Even at 60 GHz radio system at the time, the maximum data rate was just around 10 to maybe 15 gigabit per second, even from the papers. So, but as you can see here, there is no special circuit, there is no special component, but a very simple modulation scheme and a very poor receivers with no RNA. Even worse, the output power was very limited, less than 100 microwatt. But even with such a very poor conditions, we were able to get 24 gigabit per second. So all this result is actually coming from very huge bandwidth of the carrier frequencies at the time, the 300 gigahertz. So I think that it is the kind of the proof of concept for the very huge merit of terahertz frequencies for very high throughput communication system. One problem is that actually this kind of very bulky system is not we want. At least many people are thinking the terahertz system installed in your smartphone or very compact devices, as you such as you do for LTE or 5G system. So so then what is a required technology or enabling technology? So surely once we need to have devices, so maybe transistors or some other special devices such as RTD or photo mixers, a shock barrier diode, and also very advanced fabrication technology is necessary. And also also we need a circuit. Functional block is necessary, particularly the very high power and low noise circuit is very important for to maintain the good enough signal to noise ratio. And the packaging antenna is one of the serious issue for Terahertz communication system because of very short wavelengths, and also usually the material parameter is unknown. And as I said before, in general wireless communication system, all the physical layer design is based on the bandwidth limited operations. But I'm not saying the power Terahertz communication system will work in power limited region purely. But anyway, the physical layer design might be different in somehow. That's because of the different maybe channel characteristics and the wave propagation characteristics. So that probably we need to think about maybe new physical layer architectures. But anyway, in this talk, I'm going to talk mainly about device circuit and packagings. Okay, so this is quite old data, but what I want to say from this slide is, so the y-axis is now the maximum oscillation frequency of the transistor, and y-axis is years. And as far as I know, there are only 5 institutes who can provide the, let's say, Terahertz transistors. So in the United States, Northrop Grumman and Teledyne will provide hand-10 HVT devices, all based on 3.5 semiconductor devices. And important thing is that the Terahertz transistor has been actually developed 10 years ago. So another German group also they reported their Terahertz devices around 2009, and my company in Japan reported their Terahertz devices at around 2013. And the silicon germanium device now can operate at up to 700 gigahertz. I mean, actually the maximum Fmax of the silicon germanium HVT is now around the 700 gigahertz. So that at least the 300 gigahertz very fundamental amplifier can be implemented with the silicon germanium devices. And so what I like to say is Terahertz transistor has been available. And with those devices, many functional blocks such as power wideband amplifier and power amplifier has been reported 10 years ago. And some other functional block for communication systems such as a fundamental PLL and dynamic frequency divider and fundamental oscillator, all these components has been also reported. So transistor is available. So by using the transistors, we can design the circuit, and several functional block has been reported or available, I can say, and it's in research domain. So at that time, my group designed a new research program that is about a bit more full system demonstrations of Terahertz communication system in kiosk data download system, data download scenario. So kiosk data download scenario is, for example, what we are thinking is something like a data vending machine. So simply we approach to the vending machine and pay some money and select the data you like to download. Then the machine will transmit the data to your smartphone within a very short time. So we thought that such vending machine can be used as something like a poster machine, posters, or yes, posters. So it was one of the ideas, but at the time what we thought is if we now look at some movie poster in the subway train, and then you take pictures. Okay, you take a QR code with your smartphone and have some traditional transactions for payment and data selections, and then the movies or some shortcut movies will be transmitted to your smartphone within a very short time. So this was the basic scenario of the kiosk data download system. And technically, the kiosk system can be characterized with the stationary transmitter and the mobile receiver, so that we will be relatively free from the size and power from transmitter, while we need to take care of that issue for receiver. And also link distance will not be longer than the 1 meters. And also it is peer-to-peer communication link. So in overall, if you look at this, the kiosk data download system is one of the very simple configurations or applications we can achieve even with the Terahertz communication system. The problem is it really possible with the available devices? So we did simple calculations. We assume that the 10 dBm at 300 gigahertz with a 15 dB noise figures and the 10 dB system margin. And then we assumed very simple modulation schemes such as ASK. And then we plotted available data rate with respect to the total antenna gain from transmitter and receiver. And as you can see here for black line, around the 20 or 30 gigabit per second will be available, but the required total antenna gain is around 50 dBi total, mean the 25 each for transceiver receivers. So in general, sense, the 25 dBi antenna gain is quite high at microwave frequencies, but in terms of size, but at Terahertz frequencies or 300 gigahertz, of which wavelength is just 1 millimeter, then the diameter of 25 dBi horn antenna is just like your pencils, so which is very compact. So just in terms of the diameter or aperture size, it is almost comparable to the camera module installed in your smartphone. So we thought that this calculation actually validate, give us very good satisfactory of the feasibility. So here is a block diagram of the entire system we developed. The green boxes is a transmitter block, RF block, and the purple one is a receiver block. The mission of that project was to operate that Terahertz devices along with the commercially available networks such as Ethernet network system. So in order to make a 20 gigabit per second data stream, we merged two streams of the 10 bit Ethernet system, and MUX and data MUX and DMUX was used. And also for reliable operations, we developed a dedicated for the error collection board. Okay, so at the first time we developed our own transistors. So here is the photo of the substrate. So we used to use 3.5 materials. So actually the mission, one of the biggest mission when we developed the transistor was how we can anyway get the higher powers. Then we had to increase the breakdown voltage. So to do that, actually we paid a lot for frequency performance. But anyway, the maximum the Fmax was around 700 gigahertz. And then to operate the circuit at Terahertz frequencies with no problem, we need to thin down the substrate down to 50 gigahertz or even less than this, to suppress the substrate mode. Because of the high dielectric constant of the indium phosphide substrate, the electric Terahertz wave, even in the CPW or microstream line, can be easily coupled to the substrate mode. So to suppress that, we had to thin down the substrate, and also to ensure the no substrate mode in the circuit, we had to add a very dense via hole. So such a very dedicated fabrication was very challenging at the time. And based on that, anyway, we developed the power amplifiers. So to get 10 dBm out powers, we had to integrate 12 transistors in series and 8 transistors in parallel. So that in overall more than 100 transistors had been integrated in for this power amplifier. So the achieved bandwidth was 35 gigahertz The small signal gain was 15 dB, and the power was around 10 dBm. So it is a quite good number at the time. But the issue actually is if we look at these power dissipations of the transistors, the efficiency is much less than 1%. So we had to supply 1.3 watt for 10 dBm, 10 milliwatt output power. So more than 99% of the energy supplied from the DC is actually dissipated by heat. So we had to pay much attention to that heat problem during the experiment. And here's packaging. I will show the detail of the packaging on the other sections. And then the ASK modulations, there is nothing special. So we used the shunt distributed switch, to implement the ASK modulators. But one issue when we designed this circuit was the feedback capacitors of the transistors. So because of these feedback capacitors, basically the carrier signal should travel on this main branch, but because of that the feedback capacitor, some of the main pass signal will couple into the transistor and make another interference pass. So because of that, it was quite hard to maintain a very good group delay performance of the whole circuit, even with this distributed topology. But anyway, by using the series transmission line at gate, we were able to anyway control that the feedback interference characteristics. So the final achieved group delay was much less than 4.5 peak per second in the operating band, and a very good extinction ratio, on and off extinction ratio was achieved. Okay, receiver is quite, this is a photo of the receivers. And in receiver, for receivers, we integrated everything into single chip. So I'm not sure that you can see the antenna itself, but we integrated dipole antennas along with the RF amplifiers and ASK detector and data amplifiers. So all this block has been integrated in a single MMIC. And then, so basically the antenna gain of that integrated dipole antenna is not that high. So, to increase the directivity, we attach the hemispherical silicon lens on the backside of the MMIC. And then this is the first version of the receiver packaging. And when I have this kind of talk, many people ask me how we design the antennas or how we simulate such a very high frequency circuit. But as long as you have very accurate device material parameters, then the commercial HFSS or all electromagnetic simulator will give you very good result. So the most important thing is that how we get the accurate parameters. And the performance of the amplifier was more than, in terms of gain, the 24 dB gain and more than 10% bandwidth. And by using that, we had very simple data transmission experiment at very first time. So here is a transmitter chain and the receiver block. And we actually changed the distance between transmitter and receiver. And as you can see, the measured BER was much less than 10 to the minus 8 at up to 1 meter long distance. And you can see now very clean eyes. And I now prepared video clips for you. Now you can see the head of the transmitter antenna, and the receiver is now installed on the moving stage. So now this green spot indicate the distance. 9 means 0.9 meter and red 1 means 1 meter. So since the receiver is moving back in real time, so you can see now the recovered eye stream is delayed a lot. And by using those devices, actually we optimize the device a little more, and finally install that devices in the kiosk data mock-up of the kiosk data download system. So basically the transmitter is looking at upside, so installed in the body of the transmitters, and also the receiver was installed in the smartphone size mock-up terminal. And again, to ensure the reliable operation in practical scenario, we developed the FPGA-based feed-forward error collection board. That is actually based on the Reed-Solomon algorithm that requires that's because actually at the time we looked at the two different algorithms, Reed-Solomon and LDPC. But problem was that the required number of gates for LDPC was much huge rather than the Reed-Solomon algorithm. So just because of that, we used to use FPGA, Reed-Solomon based FPGA. And according to our study based on the channel propagations and algorithm characteristics, and we realized that the Reed-Solomon algorithm would provide quite comparable to that of LDPC algorithm. Of course, if we use the soft decision LDPC algorithm, then the same rate or same code length will provide, the LDPC will provide much better performance with a comparable code length. But as I said, in general, FPGA or the ADC, DAC is not available at that high sample rate, so that if you assume the hard decision conditions, then LDPC will provide a little bit worse performance compared to the Reed-Solomon algorithm. But anyway, so here is another video clip of the final demonstrations. Okay, so what he did is simply he placed his own smartphone on top of the kiosk data download system, and the first touch was about payment and data payment, and the other touch was about data selections. And after several seconds, all the data has been completely downloaded from the transmitter to receivers. At that time, the size of the data was around 7 gigabyte, so that in terms of bit, maybe more than the 50 or 60 gigabit has been transmitted in 5 to 6 seconds. Okay, so this is around the very, all right, yes, so Tom.
Professor, this might be a good time
Right,
to see if there's any questions.
That's right.
Let's see, I think we have a question from Afshin. Let me see if we can unmute. Okay.
Yeah, I'm unmuted now, right now. Thank you.
Okay.
A very interesting presentation. And I was a little bit puzzled in terms of the two detuned lasers that you were using to generate the 300 gigahertz signal. Is this the approach that you had used for this demonstration that you shared this evening, or are you using electronic way of generating the 300 gigahertz?
I see. So this photonic one is the first version of the system, and then the final demonstration is developed with all electronic devices. So I didn't show the detail about the multipliers and the signal source, but anyway, everything is electronic devices. So we use the external error signal, and here is a multiplier block, and then the modulator and power amplifiers.
Okay, and I had also a question about your antenna. You were using a dipole antenna on a lossy substrate. What was the efficiency of the dipole, and how would you be able to improve?
Right, so that's right. Okay, so first of all, we used to use first of all, the MMIC has been fabricated with indium phosphide-based HEVT. So the substrate is not that lossy. And also the silicon range at the time, of course, the silicon is basically P-type, very lossy material, but at the time, we used a very high resistivity silicon materials for this lens, so that the general idea, generally, the overall loss from the material might be not that high. And according to our measurement, the overall radiation efficiency was around 50 or 55%.
What kind of loss tangent did you consider for your substrate to end up with a very good efficiency of 55%?
That's right. That's right. So actually, we didn't look at that much detail about the loss, but anyway, in my memory, the resistance of that silicon material was much higher than the 10 kilo ohm squares or something. So that yes.
Professor, you just said the word silicon for, I thought the MMIC was indium phosphide.
Indium phosphide, right.
Okay, and that's a semi-insulating substrate, am I right?
Sure, that's right, semi-insulating one.
Okay.
I guess you're referring to the silicon lens.
No.
With 15 dB of gain, yes?
Silicon lens, that's right, yes. So including this silicon lens, this dipole antenna provides around the 20 dBi directivity. So considering the efficiency, in terms of gain, it might be around 17 or 18 dBi. But in terms of directivity, more than 21 or 2 dBi.
And you were saying that the efficiency of the receiving antenna was maybe 50%, 50?
That's right, right,
Okay.
right.
Great. Are there any other questions? Thank you, Ho-Jin. It looks like there's no other questions right now, so maybe we could continue on.
All right, okay.
Oh, wait, Utkarsh has a question.
Thanks, Tom. So, Professor, it seems most of the data you have showed, it's the modulation schemes used were quite basic. Are you, and it seems like if we go to more sophisticated schemes with higher bit numbers, you can probably even further improve the capacity. Are you working in that direction, or are you aware of any other work which is considering like higher modulation schemes?
All right, okay, so very good questions. And actually I prepared some slide about that issue, but I mean, just I will show right now.
Sure.
So after that, we developed the QPSK modulators, and that provides around 50 gigabit per second error-free operations. And then we also increased the data rate more and more with the more complicated waveform, but probably I missed a slide here. But anyway, finally, we succeed to transmit 100 gigabit per second with a 16 QAM modulation scheme. Of course, but at that time, the waveform itself has been generated with very high speed DAC or that's right, yes, 8WG. So it is not that easy to say we actually implemented all the modulators. But anyway, add up to QPSK, we have been reported.
Thanks.
Okay, let's continue on.
Okay. So, but as you saw there, so let me get back to this slide again. So as you can see here, so actually, anyway, we succeed to transmit the 20 gigabit per second data stream in real time But as you can see here, this kind of very bulky metal packaging is not being able to, that is not that easy to be integrated in very compact devices. So the most biggest challenging is, first of all, basically the waveguide structure is very good, provides very good performance at these high frequencies, but it requires the mode transition between MMIC and the waveguide. So the most simple way is to add, let's say, electromagnetic coupler between waveguide and MMIC. Then we need to have a wire bond or something, the bonding technique. But as you may know that the bonding wires actually has very large parasitic capacitance particularly at high frequencies. So electrically, physically it can be very short, but electrically it is very long. So it is quite difficult to maintain the impedance during the packaging. So what we did is we integrated, okay, this is the other's job, and our work is, okay, here. So it is not that easy. Okay, simply the main idea is because of very short wavelengths, the dipole antenna or this kind of electromagnetic coupler can be integrated along with the core of the MMIC. So this is one way in the packaging, but still we have to use very bulky metallic structures. So you know, to avoid that, we had one idea. So I said very first time, the terahertz wave is locating right between microwave and the light wave. So waveguide packaging is very traditional microwave technology, and we thought that how we can use traditional light wave device technology, packaging technology. So here is the concept of quasi-optical packaging of terahertz devices. Actually, the concept is coming from the LED packaging. So if you look at the LED packaging, what we required is, first of all, we need to have an electrode carrier. And then we should place the LED chip in the middle of that carrier, and then encapsulate that with the plastic materials, you know, to form the lens. So actually, we did something like that. We prepared the carrier or electrode structures with the LTCC technology, and then placed the MMIC I showed before, the receiver MMIC with the flip chip bonding technique on the middle of that LTCC substrate, and then placed the silicon lens again, very low resistivity, the very high resistivity silicon material lens on top of that devices, MMICs. And here is a photo of the final packaging. So as you can see here, so now this device is 300 GHz receivers, and the size is quite comparable to that of the camera module in your smartphone. And there is no degradation in performance. That's because all the electromagnetic wave or terahertz wave is passed through the silicon lens. And also the only data or some biases are fed by or through these LTCC structures, so that there is no degradations or even equivalent to that I show in metallic one. And the other idea was that the biggest challenge in terahertz devices or packaging is anyway the losses even in the waveguide structures. So fundamentally, although losses are coming from the conductive material or dielectric materials, so probably in order to suppress or in order to enhance the loss performance, we need to anyway avoid the conductive loss or dielectric loss. So what we did here is simply we made let's say a waveguide structure or horn-shaped structures even with dielectric material packaging. So this is actually the concept of the LTCC packaging, which is very common for even for 60 millimeter wave devices. So we think we are going to place the MMIC in the middle of the LTCC structures, and then coupled into the transmission line and finally radiate into the air. But the radiating structure might be fabricated as look like a horn shape. So here is a photo of the fabricated packaging. So for the test at very first time, we made let's say a LTCC horn antenna. We stacked up 30, maybe at the time 33 layers. And then the overall thickness, or let's say length of the horn antenna was around 2.7 millimeters. So in terms of wavelengths, it was around 2.7 wavelengths. And we made standard horn waveguide interfaces at the other side of the horn antenna. And then the measured gain was, as you can see here, more than 15 dBi. The bandwidth more than 40 GHz. And the more important one is that because of very these pyramid shaped structures and with low loss, we were able to get, I mean, the simulated radiation and the measured radiation pattern shows very good agreement. So And also more important thing is that this kind of structure can be fabricated with the commercially available LTCC or even other substrate technology. We don't need much very accurate tolerance. So in my memory, the tolerance of this fabrication was around the order of the 50 microns. So that surely, if you look at the detail, this step structure has been, distorted a little. But anyway, even with the defect, the overall performance was very good. So based on that, we finally, and also then the other issue was how we couple the MMIC into that home structures. So here is a concept of the electromagnetic coupling integrated in LTCC packaging. So basically in LTCC technique, so as you may know that the most important thing for this kind of the backshot structures, the length of the backshot is very important, should be tuned, to make a very good impedance matching. But in case of LTCC, we have to use a fixed thickness substrate, meaning that we cannot have fine control of this backshot length. But by using the via hole or distance between the via and these backshot structures, we can control the impedance. That's because now this, let's say, the dielectric part between the air hole and the via hole will work as something like, let's say, a dielectric shunt stub. So by controlling this shunt stub, we can anyway control the overall impedance of this backshot part, so that finally we can achieve the very good impedance matching even with LTCC technique. So here is insertion loss, measured insertion loss of that transitions. So expected transition loss for single transition was around 1.5 dB, which is slightly higher than the other transition, which is the fully integrated MMIC integrated transitions. But anyway, it is quite reasonable for considering very compact packaging side. So this is what we did for very compact packaging. And actually, I showed this one. So in previous experimental result, I showed that just 20 gigabit per second. But at very first time, if we use 100 terahertz frequencies, then the 100 gigabit per second or even higher throughput might be possible. But as I said, what we did is a QPSK modulation scheme. But probably I need to mention this. Waveform is very important for communication system, very fundamental one that define the spectral efficiency, and also it related to many other issues such as PA, PR, or non-linearity of the power amplifiers. But anyway, we now go back to the Shannon theory again, to look at what is the most, let's say, optimum modulation scheme at terahertz frequencies. So we assume that the signal SNR goes to 1 due to the very low power or very wide bandwidth operations. Then this equation can be simplified as simply all this low term will go to 1. Then the maximum data capacity of the given channel will be simply bounded by the bandwidth, which means that the maximum bandwidth spectral efficiency should be 1 if the SNR is very poor, which means that the most optimum modulation scheme or waveform is something like a QPSK or BPSK. So in that point of view, so we developed the QPSK modulators, and as I showed, 15 gigabit per second has been proved. Error-free 15 gigabit per second operation has been proved. And if we have a chance to use something like equalizer or FEC technique, then the 16 gigabit per second with single device would be feasible. And also, if we need to increase more and more, then we need to rely on the several high-end modulation scheme. But there is a very huge demerit, for example, in case of QAM. So as you may know that basically QPSK has a very constant envelope so that we can operate the power amplifier at the saturated power. But in case of QAM, because of the very high PAPR ratio, PAPR. So we need to operate the power amplifier at the back of operation point, maybe 6 dB or 9 dB below, less than the saturated power. So actually, it is a very huge demerit. Again, it is quite hard to get very high power at Terahertz frequencies, but if we now use the QAM waveform, then we need to reduce the average power from the power amplifier, or we have to use more amplifier, to maintain the equivalent or same EIRP. So actually, I don't like to use the QAM signal, but anyway, if you look at the many papers about Terahertz communication system, at this moment, many people used to use a QAM waveform, to reach 100 or even higher data rate. And one of the big challenging the Terahertz frequency is anyway we had to use the high gain antennas. So according to the previous link budget calculations, even for 20 gigabit per second system over for 1 meter long distance system, total required gain was antenna gain was around 50 dBi. But anyway, we need to think about at least 30 dBi gain will be required for transmitter and receiver. Then basically everyone know that the beam will be narrowed, and there will be some problem of the coverage or reliability, which is not practical at all. We know that we cannot use omnidirectional antenna because of the low power amplifier that can provide such high powers or gain. Then the beamforming chipset is really important. So from now on, we need to think about the beamforming chipset. So in my group these days, what we are thinking or what we are working on is kind of the co-integration of silicon and the 3.5 materials for beamforming transceivers. So considering the integration performance of the indium phosphide devices, then it is quite hard to implement beamforming, very massive beamforming transceivers with the 3.5 system. So what we are thinking is we fabricate or we develop the beamforming functionality or beamforming function in silicon devices, and simply connect the output to the indium phosphide materials for high output powers or very low receiving noise. So and also some people are thinking full silicon Terahertz transceiver. That's because these days they are using very special design concept. We are able to get some gain even at Terahertz frequencies. So for example, here is a report by one of my colleagues, and this 3-stage amplifier give us around 10 dB gain at around 280 or 300 gigahertz. So actually the main concept is, to compensate. So please note that the maximum Fmax of this TSMC 65 nanometer CMOS was around 350 gigahertz based on the custom design layout. But the most challenging was how to avoid the losses. So transistor can provide just very tiny gains at up to 300 years, but problem is that the associated loss on this maybe metal structure is not that very high. So to compensate that, actually we intentionally made some positive feedback loop, but we show that the transistor is not getting to the oscillation mode. So anyway, by using such a very tricky design, anyway, we can get the gain. And also here is another very good report from the Hiroshima University. And then this is mixer last or mixer first structures. So they actually integrated multiple mixers, to boost up, to combine the powers from the mixers. So that at the time the output power was as high as 0 dBm. And to that they integrated more than 8 mixers in the devices. But anyway, by using this kind of structures in silicon, the multiple gigabit per second data transmission has been successfully demonstrated. And also, if I get back to my work again, then the problem in this concept is that how then we interconnect these silicon devices and the indium phosphide devices. So in this concept, just I made a simple concept diagram based on the flip chip bonding, but considering the frequency bandwidth or maximum operating frequency of that flip chip bonding technique, it may not be feasible in practical. But what we are thinking now is a wafer level packaging technique. So since all the interconnection between in the packaging is based on the wafer level backend process, so that very fine pattern and very small size ball or interconnection is available. So what we are thinking now is the kind of the multi-chip wafer level packaging devices. So here is this green one is all the silicon devices, but probably I can replace one of these with an indium phosphide and make a interconnection with that very fine interconnection technique provided by wafer level technique. Okay, so let me summarize my talk now here. So I believe that in the last 10 years, from 2000 to 2010, there has been very intensive research on Terahertz communication system worldwide, but all those focus on the device side. But anyway, with a very dedicated and high performance devices, the 20 gigabit per second system or 100 gigabit per second transmission has been reported. And now probably we are ready to get into the second phase of the research. Then we need to think about what is the optimum physical layer design. And also, to make the more practical system, beamforming transceiver is very important. And if you are thinking the performance, then the silicon is ready, indium phosphide ready. Then problem is how we can integrate in packaging side. And in that point of view, wafer level packaging technique at Terahertz frequency can be one very good challenging, one very good options for us. Okay, thank you very much. This is all I prepared for you. Thank you very much for your kind attention.
Excellent talk, Professor. Thank you so much. We have a couple questions from the audience. Let's see. Harshpreet, would you like to ask your question? There you go.
Can you hear me?
Yes.
Okay, thank you for the talk, Professor. My question's about the efficiency of your LTCC horn antenna at 300 gigahertz. Could you please throw some light on what are the efficiency numbers and the performance that you achieved?
Well, actually, we didn't try to get the efficiency number at that time, but as you can see here, the measured data simulation result is actually coming from the PEC materials, but stepped structures. So simply, if we consider the losses, then as you can see here, it's around the, it must be very, very high numbers. It must be very high numbers, almost comparable to the general horn antennas, which is around the 80 or 70%.
I see. Thank you. Thank you, Professor.
So,
and here, I'm sorry, just very short comment. Please note that actually we embedded the very short waveguide structures on the input side. So because of that, now the measured data seems to be slightly higher than the simulations.
I had a question. Wait, we have another question. Let's see. Okay. Raj?
Yes, hi. Hi, Professor. Thank you very much for your talk. You mentioned that tolerances were not important, and I'm guessing that means geometrical tolerances of various dimensions and positioning of the horn antenna, for example, in this case, with location to the transceiver. were there any tolerances associated with surface finish, material conductivity, and issues with LTCC as a substrate and its lossiness?
Okay. First of all, I didn't mean the tolerance is not important, but tolerance is important. But what I want to say is the tolerance of this verification was around the 50 micrometer range, and such a high tolerance was not that critical issue in this case. So, and also it is not clear the dielectric, what is it? At the time, the LTCC, what we used is dielectric constant was around the 5.5, and the tangential loss was expected to be around the 0.05 to 0.01 or something, not that good. But basically, in these structures, all the materials are covered with the metal structure, so that we don't need to worry about the dielectric losses. Also, and also, metal finish was basically is a standard LTCC technique, but finally we made a gold, what is it, the printed gold. So simply we made a silk screen based silicone, I'm sorry, the silver metallizations, and then finished with the same again, the print based gold material. But it is not clear the material parameters detail. And since we are used print-based metallizations, so the metal surface was not that good. I expect that, but not that bad. Well, anyway, it is coming from the standard LTCC verification provided by Kyocera.
I see. Was the metal roughness included in your simulation?
No, in simulations, we simply use very clean body structure.
Okay, thank you.
Professor, I had a question about, I didn't quite understand the wafer scale packaging proposal that you had. Could you go to that slide?
Yes.
So is there a multi-chip communication indicated in the I'm kind of confused. What in this picture here we have green, which represents some chips, and then maybe some underlying substrate. Is that right?
Right.
Okay. And
all right. Go ahead.
could you elaborate?
Okay, I will give a little more detail of this slide. So anyway, first of all, in this picture is the multi-level packaging, but not, I didn't, actually this picture didn't indicate the integration of silicon and 3.5, but anyway, please, it will give you the concept of the multi-chip packaging. So this green line is, let's assume that this one is, let's say, a silicon beamforming transceiver or receivers. For example, here is a 1, 2, 3, 4, 5, 6. Here is a 6-channel transmitter and 2-channel receiver silicon chips. And in order to make massive antenna structures, simply we need to use multiple transceiver or receiver chip on the same maybe PCB or same anyway the antenna body. So in this concept, what I suggest is if we can use multi-chip on the same plastic packaging, then we can easily configure the, let's say, a massive array antennas. Mm-hmm. So this actually, the blue one indicate that the reference error signal. So for example, the 25, let's assume that maybe about low frequency signal is injected into the feed to these chips, and then the internal multiplier will generate the Terahertz signal, and then that will be radiated through the antenna's own packaging. And if you look at, for example, in this diagram, this blue and the yellow metallization will be formed on the packaging. So once we fabricate the silicon chip, and then move it to the packaging line. But basically, all the packaging line is on the wafer level fabrication, which means that it's based on the stepper structures and the materialization, or is it the tolerance is as good as the silicon EOL.
Okay, okay, I understand. I think. Yes, so it's the means at which this multi-chip module substrate is fabricated is with wafer scale methods.
That's right. That's right. So here is the other actually example. This is the packaged module of the SORI fabricated. I mean the developed by Google. So as you know that the gesture sensor.
Yeah.
This is not the multi-chip packaging. So this is a single chip and the multiple antennas for transmitter and maybe receiver here. And what I'm thinking is simply, I like to integrate, or I like to add one more chip along with this in this one black, let's say a package body. So that is not that easy because this simple chip is not that fabricated individually. We fabricate this on wafer level with a massive number of devices. So, and then we quote the EMC, simply the compound molding mold structures, to fill up between the chips, and then the make metallizations or making forming this kind of soldering ball on wafer level entirely at once, and then finally we cut it out. So the multi-chip packaging is just a matter of how we cut on wafers.
Okay, thank you.
So, Professor Utkarsh here, related question. If you go to the previous slide where you had a plot of, so the plot you're showing there, is that measured or simulated data?
Oh, yes, actually, yes, important question. So I didn't talk about in detail, but in this case, the most important one is that, but anyway, what is the interconnection loss between this, let's say, a package level interconnection? So basically, this is a simulated result, but recently, actually, we measured the performance, and which is quite comparable to this one. So upon our measurement, the transition loss was not that good. So it measured loss was around 1.5 dB at 140 gigahertz, but S11 or reflection was much better than this. So we are now designing some other structures for via hole. So anyway, we believe that this wafer level metallization will provide a very good performance at up to 300 gigahertz. And also, this is also one of the standard fabrication that provided by TSMC or Samsung or Infineon.
I see. Okay, thank you.
Thank you very much for your excellent presentation. And I had one question regarding this particular slide. You're talking about the fact that you're going to have a 25 gigahertz reference, that it is being inputted to a multiplier chain inside every single chip that you have. And that sounds like generating a 300 gigahertz, you need to have a multiplication factor of 12, which adds about a minimum of 22 dB of phase noise degradation. And since you're looking at the QPSK modulation format, have you looked at the limit that you can have in terms of the efficiency of your modulation, rather than having a QPSK going to the 8 PSK, for example? What kind of limits are you going to deal with in terms of the phase noise degradation using this concept?
Thank you. It's a very good question. And actually, I didn't make detailed calculations, but one general concept I have now is fundamentally phase noise limit the best performance of the system, particularly in QPSK or any phase modulated waveform. But when we increase in case of the very huge bandwidth signal or waveform, the noise contribution coming from the phase noise is much less than the white noise of a very wide bandwidth. So actually, when we there is no slide. This is not my result, but it can be probably I can explain with this. So if you look at these constellations, you probably see that all the points look like just a circle, not a donut shape. And I'm sorry, not the linear shape, which means that, as you may know, that if the system is limited by the phase noise, then the most high signal should be look like this line shape on the diagonal directions. But since the system bandwidth is so huge, more than 10 to 20 gigahertz, so that the integration of integration of that white noise is much larger than the phase noise. So according to my experience, yes, phase noise is very important, but in general cases, I mean, when you transmit the signal over the air, so that once the SNR is derated a little, then all the measured result is actually limited by the white noise. So actually, I didn't pay much attention to the phase noise at this moment. And also regarding the 8PSK, so currently in my group, we now have a one link setup, and in that setup, the 8PSK was not that challenging. I mean, we were able to get the error-free transmission with the 8PSK. That is based on simply the key site signal generators, 20, maybe 8 to 5 any gigahertz signal generators. So I cannot give you specific numbers in terms of phase noise, but the 25 gigahertz key site signal generator with handmade multiplier will give you not that bad phase noise. But more important one is that I believe that the current limitation is not coming from the phase noise. So that we are now try to enhance the noise level first, rather than the phase noise.
Thank you. Could I ask one more question as well?
Yes.
Okay. As you know, NTT-Atsugi, and in particular, before leaving NTT and going to Osaka University, Professor Nagatsuma had demonstrated already in 2002 a 10 gigabits per second communication at 300 gigahertz using the optical technique.
Yeah.
And also, he has demonstrated in 2014 a longer distance than few meter in terms of terahertz communication system. Your approach being more close to my heart in terms of the microwave technique and in terms of the overall competitiveness of the electrical solution versus optical solution. Do you have any kind of opinion in that respect?
All right. Professor Nagatsuma was my boss at the time, and we worked together for a long time from photonic devices and electronic devices. And I hope you know that we don't have, actually, including Professor Nagatsuma, we don't have a specific taste about the photonic devices or electronic devices. Just we think that according to the applications, the photonic devices might be helpful, but the merit of photonic approach is we can simply use the fiber network. It is quite easy to be incorporate with the fiber optic network and or feeding network. So actually, at the very first time, we thought that the kiosk data download system will be, we thought that it should be developed with a photonic technique rather than electronic one. That's because, as I showed before, transmitter is stationary, and then that should be fed by fiber optic network such as Ethernet system. So in that point of view, the photonic transmitter is very advantageous. But on the other hand, the photonic devices cannot provide that much high power, as high as maybe 10 dBm or even 0 dBm is very challenging, which means that even if you use a photonic devices, once the power amplifier should be used for high enough power, even worse, we can implement the transmitters with photonic technique, but we cannot implement that receivers with photonic technique. Photonic device should consist of first antenna and maybe front-end amplifier, but front amplifier cannot be implemented with photonic devices. So in that point of view, there are very serious limitations in photonic devices. So it might be easy. I mean, in general, I think that the Terahertz communication system will based on very fast electronic devices, but only for the signal source particularly. Partly it can be based on the photonic technique. If we need to distribute the very high frequencies over long distance, such as again the front haul or long haul system, then it might be quite difficult to, install the 300 gigahertz signal source at every site. Then if it is, then we can feed that through the fibers, which is very low cost and reliable, and yes, very low loss. So I'm thinking something like cooperations between these two techniques rather than standalone.
Yes, and I'm sure you're also well aware of the Hosaka-san's as well as Kano-san's effort
Yes.
at NICT,
Yeah.
that are all optical-based approaches. And in particular, Professor Razegi at Northwestern has also developed room temperature QCLs and quantum cascade lasers that are extremely efficient, and they can operate from the optical technology viewpoint much higher frequency than 300 gigahertz. So there are a lot of challenges that are being brought in from optics, and I'm sure with the electronics are also a number of important challenges, as you have discussed. In particular, I was very much interested in your design of a 50 micron thin layer of indium phosphide with the vias to create the electromagnetic band gap engineering to avoid any kind of surface modes. Did you apply the same kind of methodology for the chip level design that is going to be fully integrated with the LTCC as well?
In LTCC, no. So the tolerance, the required tolerance was not provided from the LTCC technique, so that we cannot apply that. But what we realized that is the same concept. The slide. Okay, here's maybe no, here's. So I said that, so we can insert the via hole. So as you said, by using the periodic structure of the via hole, we can suppress the substrate mode or surface mode. There is one good, there is a necessary, sufficient maybe condition. We can satisfy the sufficient conditions. But in LTCC technique, we were not able to do that. I mean, such a dense via hole was not provided in this technique. So what we realized is that we can use this via hole itself as a frequency impedance tuner. As I said again, anyway, this redundant, LTCC dielectric will work as a shunt stub. And then by using the, accurate position of, by designing the accurate position of this via hole, then we can control the impedance of the given structure so that the overall bandwidth is limited, narrowed, but anyway, we can maintain reliable operation within certain frequency band. Here is another example. So for example, we try to make simple waveguide structures with the LTCC technique, so that the metal wall should be provided by the via hole in this technique. But as you know that the via hole cannot be actually made on right surface. And also that distance or density is not that high enough. But by accurately controlling the position of the LTCC via hole, for example, here, the D is now a distance between, let's say, a waveguide surface, inside surface, and the first via hole. Then by controlling this distance, we can change the, let's say, bandpass region of the waveguide structures. As you can see here, the overall design was designed based on the WR 3.4, but if we, control this D, then we can change the bandpass region. So maybe green line, you know that the 0.18 provides a high frequency band, and another high frequency and low frequency band, and with the optimal numbers, we were able to get the the optimum frequency band at around the 300 gigahertz. So what I'm going to say here is that substrate mode was not controlled with the periodic structures, but in this case, by using, let's say, impedance engineering, we were able to anyway control the parasitic mode.
Thank you, Professor. Would you be willing to take, we had a question, but I guess they've dropped there. Darren, did you want to ask a question? I can unmute you if you'd like to ask, if the professor would take another question, but.
Sure. Thanks for taking my question, and it's a really great presentation, Dr. Song. Thank you very much. I just wondered, you presented a slide earlier with the 300 gigahertz ASX receiver slide, and I had a question about its construction. If you could tell me, is this a single substrate, or was this multiple parts and connected? I couldn't quite make it out from the slide.
I'm sorry, ASK receivers.
Yeah, there was one slide. I think you called it an integrated 300 gigahertz ASX receiver. It's basically you had an on-chip antenna, and that was what.
Yes, right. I said this one. You mean?
Yes. If you could kind of elaborate on that. Is that a single sort of one-piece structure, and how I was trying to see how the antenna, the dipole antenna, was connected up to your amplifiers.
Right. So this is a dipole antenna, and I used to use the balloon here, and then made it the single-ended one, and then all the amplifiers are single-ended, but it changed it to differential after detectors, and then the output, final output, will coming out in differential way.
And that's all on one chip.
It's all in one chip.
And that's is that indium phosphide?
It's indium phosphide, right?
Very good.
Okay, that's exactly what I wanted to know. Thank you very much. It's a very nice slide. And I assume we get these after the conference somehow.
The slides will be made available in the coming days. Yes.
Okay, great.
Okay. Thank you so much, Professor. I think we'll now turn it over to our sort of concluding remarks. We really appreciate this amazing talk. Thank you so much. We've all learned so much. Really appreciate it.
Thank you very much for your attention and your interest.
So can you guys see my screen now?
Yeah, we see.
Yeah. So yeah, just on behalf of the chapter, we wanted to thank Dr. Song for an excellent talk. We had well over 300 folks registered for the talk, and in the live talk itself, we had 83, so we did pretty well. So thanks again, Dr. Song, and also wanted to mention, it seems like we had very good audience interest and participation, so always the sign of a good and interesting talk. So with that, I would like to present the last couple of slides here. For that, I would like to ask our secretary, Mr. Venkata Gade. So Venkata.
Yeah, thank you, Utkarsh. Thank you, Professor, for an excellent talk. Okay, so for the MTT-SCV 2022 officer nomination, the nomination period will begin. Is actually begin, and it's through the end of September 2021. If you are a MTTS member in good standing from the Bay Area and wish to serve as an officer, please contact jbandwidth, and the email is jbandwidth@ieee.org, with the following information, which includes your name, the position that you are interested in, IEEE membership number, your phone number, and email address. At the conclusion of today's talk, so we are proud members are the part of the Institute of Electrical and Electronics Engineers, and our tagline is Advancing Technology for Humanity. IEEE and its members inspire a global community through highly cited publications, conferences, technology standards, and professional and educational activities, just like the one we had today. The Microwave Theory and Techniques Society focuses on the theory and applications of radio frequency, guided wave and wireless technologies. Support us by becoming a member. Join IEEE, and the IEEE membership link is given here on this slide. Also join MTT-S chapter, and the link for the MTT chapter is given also on the slide. We have the hashtag on LinkedIn, MTT-SCV. Subscribe to it and follow us on LinkedIn as well. Thank you everybody for the participation, and have a good of the day and night. Thank you.